Hey guys, my name is Andrew, and today I want to talk to you a little bit about what the OpenMined platform is about and the kind of the techniques that we want to use to decentralize and encrypt the training of machine learning models. In this talk, what we're really going to be going over is just the main concepts and really the drivers behind the OpenMined platform so that when you finish this talk, you understand all the major moving parts, the justification for those parts, and most importantly, the problems that we're trying to solve. So that as we encounter different obstacles, be that in performance or in kind of cryptographic problems or incentive problems, that you know like kind of the mindset of what we're really trying to do with this platform and with this kind of research effort that's around it. So yeah, without further ado, let's get started. So the first thing I want to talk about is the business model of the typical AI company, right? So most companies that are involved in machine learning of one sort or another have to go through these three steps. The first one is they acquire data about people. The second is that they train a model that does something useful using that data. And the third is they sell the use of that model, often in the form of an application, right? Now they might also sell the use of that model in the form of ad tech or some other delivery mechanism. But the idea is that data is this natural resource that people are generating. However, there's a few problems with this business model that we want to try to address using the tools that we're building in OpenMined. The first is privacy. By definition, a part of this business model, this first step of acquiring data about people means that people are losing control of their data, right? So when a firm acquires data, they are paying or somehow coercing or persuading people to give them a copy of their data about things going on in that person's life. And when people lose control of their data, when they lose basically them owning the only copy of their data, this exposes them to several risks, right? Theft, resale, embarrassment, persuasion. And that persuasion one is the one, like advertising and that kind of thing is what that's really used for. And that's a huge issue. That's the main driver behind why I want to build this platform. And I think that it's a highly relevant issue, and it's only becoming more important as sensors like Internet of Things and smart home technology and wearable health tech become more invasive. And actually, on the inverse side, the delivery mechanisms for things like persuasion become more compelling as VR and AR become more mature. So the second one is lost natural income. So in an ideal world, we as a population are creating this natural resource. Like every person that has a smartphone is creating a little bit of this intensely valuable natural resource. However, most people that I know don't have any way to actually receive value from that resource, right? To actually be able to monetize that resource. And so we consider that to be a problem, right? Most of the time, your data is just simply taken from you in exchange for some free social app, right? The ability to send photos to your friends, and that's really not something that we think that is right, and we think that's a problem that we want to try to address. Third is the sensitive product problem. So let's say you wanted to train a model that helped with a particularly personal issue. So things like psychological issues or social issues, relationship issues. Like if you want to train a model that was going to predict when someone was having maybe suicidal thoughts or when someone was dealing with an eating disorder, in order to do that, in order to train that model, you would have to have data that is so unbelievably invasive into someone's life, right? You would have to know, their eating habits, what they're talking about with their friends, what things that they might be mumbling when no one's listening, right? These kinds of data points are so intensely personal that it there's a strong headwind to building some of these products that are the products that really matter, right? The services that really matter. Think models that help people with their relationships and with just life and being human. And and I mean this extrapolates out into healthcare tech and a variety of others too. But what I would what we would like to see in this platform also is that it is easier for startups, for people wanting to build products, to actually address some of these more personal issues by making it possible to train machine learning models on data while it stays in a private state, while people are still inherently protected. And finally, the final problem we want to address is the aggregated power. So right now, aggregating data into kind of a central location sort of gives a few big players most of the control, most of the ability to train these powerful AIs. This is I think that saying data is the new oil is a really powerful analogy to the extent that models are free. Like, they make great news and great headlines when they come with a new type of machine learning, but truth be told, the data is what actually is valuable. That's the competitive advantage. And right now it's aggregated into a few central locations, and that kind of creates a pretty significant power dynamic that I think we'd like to address. So the success criteria of this project are really the inverse of that, right? So we want people to be able to protect their privacy. We want them to be able to earn a passive income. We want to see the development of sensitive products. We want decentralized power. And finally, we want something that is a little bit additive. We want whatever approach that we take to still be productizable. We still want it to be able to facilitate the creation of products and services that can have all the oomph and the incentives behind them that the capitalistic machine that we live on, frankly, drives. If we somehow lose the ability for people to start businesses, to do startups around this technology, we will lose a lot of the incentive for adoption, right? So that's kind of an interesting sort of criterion that we want to make sure that we stick with. So the outline for the rest of this talk is going to be in two parts. The first, we're going to address ingredients for a solution, because if we jump straight into recipes for applications, we jump straight into what the OpenMined architecture is about, I don't think it would make sense to the vast majority of the people watching this video if at first we don't establish what the main ingredients are and all agree on the same terms we want to use, right? So we're going to talk about deep learning, we're going to talk about federated learning, we're going to talk about homomorphic encryption, and we're going to talk about blockchain smart contracts. Cool? So let's jump right in. First, what is deep learning? Deep learning is a way to train a model that learns to convert one data set into another data set, right? So in this case, we say data set A and data set B. Now this might be, converting Monday stock prices into Tuesday stock prices, right? Or it might be converting, a data set of MRI scans into a data set of whether people have cancer, or whether people have a broken bone, or whether people have something else, right? So it's fundamentally, I have an input data set of data that's readily available to me that I can always collect. And I have an output data set of things that are harder to collect, things that I want to know, right? Whether someone has cancer, whether the value of the Apple stock is going to go up tomorrow, right? And I'm going to train a model that learns how to convert one into another. That's the essence of the goal of deep learning, right? Now we call it deep because it's got this hierarchy and this nesting, but at a high level, what you really need to know, if you're working on a different part of the OpenMined platform and you're like, okay, what is this deep learning thing? It learns how to take one data set and transform it into another data set. And deep learning just tends to be the class of algorithm that has been incredibly successful in doing this over the last few years. And it's called deep because of this. See, if you see these layers of different weights, these are actually layers of weighted sums with a function applied to them. It turns out that there's kind of this interesting hierarchy that can be learned inside of these weights. So how does deep learning work? Well, it works, I think the best analogy, or the best description is just say it works by trial and error. So you actually create a random series of additions, multiplications, and then a couple other random functions, right? That are these kind of curves. And so you create it random, and at first it predicts totally randomly. But what you do is you take one sample, so one row of your input data, right? So maybe it's Monday stock prices, and you say, okay, random function, take this piece of data as input and output a piece of data, right? Show me what the output is. Like if you have a function, data comes in, data comes out. And the input, the middle parts of that are starting out random, is what we established, right? So we have this initialized random function, we make a prediction, then we compare that prediction with the true value. What was the actual stock price on Tuesday? Was it higher? Was it lower? How well did our prediction do? And then we're going to tweak the function to reduce error. Now let me show you what I mean. So if we have an image that's a picture of puppies, right? So with puppies.jpg, we make a prediction and it predicts cat, right? So that's our predict step. Then we have this compare step. Okay, cat does not equal dog. It was a picture of puppy, so the label should have been dog. So what we do is we look at all these different little pieces of the function and we say, okay, how should I change? Should I move this number up and down? Should I move this number up or down? Should I move this number up or down? And I basically just kind of give it a slight bump in the right direction so that next time this random function will predict dog with a little bit higher probability, right? And if I do that over and over and over again, eventually it will learn how to transform pictures of puppies into the label dog. And that's kind of the essence of sort of the API level activity that's going on in a deep learning model. So if you want to play around with deep learning, check out some of these popular libraries. I personally am a really big fan of PyTorch, but I mean, all these are really, really great frameworks that have had very significant adoption. So yeah, go ahead and check those out. All right, federated learning. So our second ingredient that we want to learn about is called federated learning. And this one is a little bit less well known than deep learning, but it's incredibly powerful. So federated learning is machine learning over a distributed data set. So normally, when you wanted to train a machine learning model, right, you train it on data, and what you would do is if you're a company and you're training a model, you would buy data from a bunch of different places, maybe from a bunch of different users, right? You'd get a bunch of users to all collect the data on their smartphones and send it to you at a central server, right? And at that central server, when you collected all the data into one place, you would train your machine learning model, right? Because you need the model and the data to be in the same place, and it's really easy to just kind of bring it all to a server and do your work there, and then you're done, right? Federated learning says, wait, we want to do it the other way around. Instead of bringing the data all to one place, we're actually going to take the model to each individual data source, right? So in the research that Google and Apple do, for the model that actually does autocorrection when you're texting, right? So sometimes it works, sometimes it doesn't. But when it's helping predict what the next word is you're trying to type, that model has been tested using federated learning. The training of that model has been tested with federated learning. And the idea is that instead of taking all of your texts and aggregating them to one spot and training the model, they're actually sending the model to your phone. It learns on your data, then it goes to someone else's phone, it learns on their data, and it goes to someone else's phone, learns on their data. That's generally how it works. So the steps are much like machine learning, but it's a little bit different because of where the data is located. So first, users download a model, and then users train the model on their own data, right? And then they upload what's called gradients to a server, and we'll talk about that in a second. Gradients is subject privacy, and the model's updated to the cloud. Okay, so what is this gradients thing? It's the first time we talked about this. So we'll go back to the deep learning slide, right here. Okay, we first made a forward prediction. Then we said, okay, cat does not equal dog. And then we wanted to learn. Now, when I said, we have this function, it's a series of additions and multiplications, right? And there's some fixed numbers in here, and those are called parameters, right? Those are the parameters are basically just a big lists of numbers, right? So they're matrices and they're vectors, but you can think of this big list of numbers, and those numbers control how this network makes predictions. And when I refer to gradients in a federated learning context, what I'm saying is the gradient for this number right here. So every line actually has a number on it. You can't see it, but that's how these deep learning models work. And if I think that this little number should go up, then I have a positive gradient of 0.1, 0.2, 0.01, something like that. Down is a negative gradient, like negative 0.1, negative 0.25, negative 10 if it was a really big gradient. But what gradients really represent is how much I want to change each part of this random function, right? So it's just the diff between what the neural net was before and what I think that it should be, so that it's more likely to predict dog next time, okay? So we're in this federated learning concept. Instead of people uploading the whole, users download a model, right? So let's say each user has their smartphone and it's generating a little bit of data. They download a model, they train the model a little bit on their own data, and that generates a diff or a gradient that says, okay, here's what I think the model should be, so that it'd be slightly more accurate. Instead of sending the whole model back to the central source, they just send that diff. In this case, we call that gradients. And that's how federated learning works. Now, as far as federated learning platforms, unfortunately, there aren't really any open source federated learning platforms that I know of, and there certainly aren't any that are kind of widely known and accepted within the industry. The main ones that the research seems to revolve around are kind of internal at Apple and Google, often centered around kind of updating models that are run on people's phones. Okay, so the third topic we're going to talk about, a third ingredient, is homomorphic encryption. First, we're going to talk about what is homomorphic encryption. Then we're going to ask how it works. And then we should be able to see a small Python demo from scratch, although actually I'm going to skip that in this talk because I don't want to do anything that's tied to a specific version of a piece of software, because I want this video to kind of be self-standing for a long time. So we're actually going to skip the demo. But first, what is homomorphic encryption? So I think this slide pretty much sums up the capabilities of homomorphic encryption kind of all in one spot. So you can take the number 3, you can encrypt it using this magical encryptor, and then it generates this series of ones and zeros. And it doesn't have to be ones and zeros; it can be something else. But basically it's a bunch of gibberish, right? But in a numerical form. And the interesting thing is that the way in which it's encrypted allows you to do mathematical operations on this gibberish in such a way that it decrypts the value of whatever those mathematical operations were. So if I take 3 and encrypt it, and I say 2 times that encrypted value, the decrypted value will be 6. Okay? Or I can take 2 encrypted ciphertext, two pieces of gibberish, and add the values of that gibberish together, and it will actually add the value of the encrypted numbers together as well when I decrypt it. So the interesting thing here is that this means that we can perform computation on numbers that we don't know the value of, right? So someone can encrypt a 3 and a 5 with this encryptor, generate ciphertext A and B, and give this to someone else, right? They could upload it to the cloud, to Amazon. They could give it to their friend. They could give it to an enemy, right? And that enemy could perform some service, right? Or that cloud node could perform some service by doing some mathematical operations on the ciphertext. And then they send the result ciphertext back, which then gets decrypted into the resulting value. And the cool part is that you can perform computation on values that you don't know the actual value of, right? And that's sort of the big pitch for homomorphic encryption. So, and we'll show you how this fits into our system later. Now here's a few interesting libraries you can play with for homomorphic. And I'll make these slides available too. All right, finally, smart contracts. What is a smart contract? What is a blockchain? How do blockchains work? And how do smart contracts work? So first thing, what is a smart contract? Smart contract is a data set stored on the blockchain, and that data set contains 3 things. Data, which is just sort of like historical data, kind of arbitrary data, anything you want to throw on there, right? So you can think of the blockchain as just a big database. State, which means today's data, right? So it's data with a particular date attached to it. So we might say that the state of the world right now, today, is that Apple stock is at X number, and the president of the United States is Donald Trump, and random other things that are all associated with data points that are happening today, right now. So that's what state is. So data is like the big archive, or just things that don't have dates, just arbitrary data. State says data at today's date, and then code are rules for changing state, right? So some things about state are read-only, right? I can't change who our political leaders are or something like that, but I can see what it is. But however, we can also write code that says, okay, given today's state, how can I change tomorrow's state, right? Or how can I update this to be managed in a particular way? And that's what smart contract is. But in order to understand why this is important and why this is cool, we first need to understand what a blockchain is, right? So a blockchain, first and foremost, is a large distributed data set, right? So it's thousands and thousands of machines that all have exactly the same copy of a data set. And they store it in such a way where a few things are true. First and foremost, no one person can edit or delete an old entry in the data set, right? So you can only add to the data set. You can't delete anything in the middle, okay? No one can fake a new entry, right? So I can't write something on that someone else thinks, in lieu of someone else. Like I can't claim that another person wrote something into this data set that they didn't write, right? So each person's contributions to the data set are recorded. And it's recorded, who's also making this contribution, and these two kind of axioms are enforced by the fundamental limits of computation in the most popular framework, which is called proof of work, and there are a few others as well. But the big thing to take away is that no one can edit or delete an old entry. You can only add to it, and no one can fake a new entry in someone else's name, right? Cool. So now there's this really cool demo from this guy named Anders, and I really want to actually show you this because I think that it's just the best way to actually show how blockchains actually implement this. Okay, so what I want to do, there's this really awesome blog post, and feel free to go play with it yourself. But it's a demo, and I think it's easily the best demonstration of what blockchain is really all about. So first and foremost, blockchain starts with understanding what a hash is. And what a hash is well, it's this thing down here. Big random sequence of numbers and letters. And if I type in an A, B, C, D, basically what it does is it performs an operation on this data such that the result is a seemingly random sequence of numbers. However, so you can see this 88D4. If I delete this and I type A, B, C, D again, it's 88D4. So it's seemingly random, but the truth is that it's entirely deterministic based on whatever data I put here. No, anyone in the world, if they use this particular hashing technique, could type in A, B, C, D, and they would end up with this exact same hash, okay? So if I type a bunch of other gibberish, right? 207B, right? 207B, like that's how the hash works. And notice it's a fixed length, so it's always exactly the same length. And there's no way for you to actually go backwards. You can't look at this and then go, I wonder what the data was that created this hash. Like you can only go one direction. You can only go from the data to the hash, which is kind of an interesting property of these hashes. Okay, so now a block, and this also is the inspiration for the term blockchain, is basically based on this idea of a hash. Okay, so everything in this block is considered the data. So we have a block number, we have this thing called a nonce, which is really just another number, and then we have some arbitrary data field, which could be, a bunch of tweets, or it could be my bank balance, or it could be today's news, right? Now, there's also an interesting thing down here with this hash. Notice this hash has 4 leading zeros, okay? That's very peculiar. And more importantly, when I type something here, it sort of rehashes this whole thing, and all of a sudden I don't have 4 zeros anymore. So this opens the notion of mining, right? And what we're really going to try to do, we have this sort of arbitrary task, and what we're going to try to attempt is, given some data that we put in here, we're going to try to increment this nonce, right? We're going to start at 0. We're just going to find a nonce wherein the hash of the whole thing, the block number, the nonce, and the data, leads with 4 zeros, right? Now the odds of that for any individual one is pretty small, but after a while you'll find that we can actually find one. So what it's going to do is just increment this nonce until the first 4 characters are 0. Sometimes it takes a minute, and perhaps the most important part is that it does take a minute. Okay, we found 4 zeros. So the interesting thing here is that it actually takes a certain amount of time to find a hash that has this property, right? We have to, add 1 to nonce, hash the whole thing, see if there's 4 zeros, and repeat. And do that over and over and over again until we find one that has this particular value. And the more zeros that we required it to have to go find, the longer it would take to, quote unquote, mine the block. So that brings us to what a blockchain is. Okay, so if this is one block, a block is validated or mined. When we find a nonce that generates these 4 zeros, a blockchain is based on this idea of a block. And the idea is that we're going to have a series of blocks that are linked together, and the hash for each is generated based on 2 things. First and foremost, the contents of the block, so the block, the nonce, and the data, right? As well as the previous block. Now the first block just uses all zeros for the previous block, but what this means is that if I change the data here, when I hash this, it creates this hash, which is not a valid hash because it doesn't lead with 4 zeros. We haven't mined it yet. But because I've changed this hash, that means this block, which is connected to it, generates its hash using this hash, which we also haven't mined yet. So in order for us to actually discover and to kind of mine this chain, well, we need to first increment the nonce of the first block to find a hash that leads with 4 zeros. And then once we have that hash, we're going to have to mine this one because this one's hash is also based on the previous hash, which we just now discovered. There's kind of this dependency chain as we walk through the blockchain. So first, let's mine this one, okay? Mine. Okay, we found nonce. Looks like it's nonce, 11,551. That actually worked, okay? Now, some more data, okay? Now, this thing is going to hash, meaning generate a random value for the block, the nonce, this data, and the previous hash. Notice how it's identical, B74, B74, and we're going to mine it. Ooh, it's taking a while on this one. Okay, and then let's just do a bit more data, just to do one more time. Now the interesting thing is that because it's mined in this particular way, I know that it's incredibly difficult for someone to go back over here. Let's say that they change some data. Some different data. Not only did it corrupt this hash, right? It unmined it, right? But it also corrupted every later block. And the interesting thing about it corrupting every later block that means that in order for us to have valid blocks, blocks whose nonces are set to the correct values such that the hash begins with 4 zeros, we have to remine it again. This is incredibly expensive. So what this does is this means that it's incredibly easy to verify that an entire chain is interlinked together, right? And that someone took the time to mine this one, and then mine this one, and then mine this one, right? And if anything in here became changed, it would corrupt all the rest of these hashes, and we would have to remine it in order for them to become quote-unquote valid. Now, the interesting thing about doing this distributed is this is done across the network. Different people can mine some data, right? So a bit of data, some more data. We're going to mine this one as well. We're going to mine the first one, and then what we're going to see is that two individual people can come up with independent chains, right? So mine this one. We say a bit of data. We use the exact same data set, right? Because in theory, they should have the same data set. And then some more data. And here's the cool thing. When you compare this hash, 578, with this hash, 578, both of these guys know that every block in their chains are identical because these two hashes are identical, right? So they can both look at each other and go, hey, we have perfectly valid chains where we've both done the exact same mining procedure. And not only that, we know that every single entry leading up to this block that we're on, block number 2, is identical. Because if I were to change this, it would change this hash. Not only is it not valid, but even if it was remined, it would not mine to the same value as here, and they would know that, even if there's a billion blocks before this, you would know whether or not the two blocks are identical. Cool? So that's the essence of distributed blockchains and why it becomes easy to tell whether or not two chains are the same. Now, the real question is, how does this kind of prove these axioms we were talking about before, where no one can edit, delete an old entry, no one can fake a new entry? So what this really solves for is no one can edit or change an old entry, right? Because if, let's say, this guy wanted to change one of these old entries, right? So we've mined this one, a bit of data, mine. Almost there. And then some more data, so this should be 0082. Okay, some more data, perfect, awesome. If this guy, and so if let's say we have 3, right? A bit of data, some mine this one. So we have 3 different chains. Takes a second to mine these guys. I'm gonna zoom out a little bit so you can see more of these. Some more data, right? So now, we have 3 chains that each required a non-trivial amount of work to generate. And we know that they're identical because we see 578 here, we see 578 here, and we see 578 here. These hashes are identical. So now let's say this guy wanted to change an intermediate data set from before. My change. Here's how we know that he changed it. First off, we have these 2 guys say, wait, no, your hash should be 578 at block 2, right? So we know that it's different, but we don't necessarily know which one's better. So the way that we measure which one is better is we look and see who has the longest chain. So these 2 people have the longest chain, which means they've been basically in agreement or corroborating each other, more or less, for the longest amount of time. So the fact that this guy tried to change a piece of data before meant that in order for him to actually catch up and have the longest chain himself, he had to remine each individual block. And that is what makes it incredibly difficult under the what's called proof of work scheme for someone else to interject data older in the blockchain. Okay, so that's the essence of a blockchain. There's certainly more details to make it work in a distributed consensus way, but that's kind of the mechanism that allows blockchains to make it so that it's difficult for someone else to change state. Now, smart contract, on the other hand, is basically when you store data, state, and code on this blockchain. So you have this unified data set that everyone can see, that is able to manipulate itself, right? So code can actually execute state, and because that code is deterministic, everyone can agree on what the data set was, and everyone can see what the data set should now be given an updated state because everyone has already pre-agreed on the code that's actually being executed and the code is deterministic. So the idea of a smart contract is now we have this shared computation that lives out in the cloud that no one can corrupt after having uploaded the code, which we all kind of can see and agree on and have consensus around, right? So this means that you can have programs that run on their own that in theory no one can corrupt at the last minute for their own interests, right? And these programs can exchange money or maybe run a little machine intelligence or do kind of arbitrary programming things. But the cool thing is that it's not under the independent control of like one central authority, right? Who can stop the code or change the code or do whatever. It's pre-agreed upon code executing out on the blockchain that is enforced via consensus and via this kind of proof of work algorithm. And there are other algorithms too other than proof of work, but that's kind of the most famous. All right, so now we've walked through a lot of ingredients, and I hope that you feel like you at least have kind of a strong appreciation for them. In the next section, what we're going to do is look at how we can combine these ingredients to accomplish the goals we were talking about at the beginning of the talk. So first, let's review the AI business model. The AI business model acquires data about people, and then it trains a model based on that data, hopefully to do something useful, and then it sells the use of that model, often in the form of an application. The problems we wanted to address were privacy, lost natural income, and the sensitive problems. So we want to mitigate privacy, we want to generate natural income for people, and we want to be able to facilitate the development of sensitive products. So our ingredients were deep learning, federated learning, homomorphic encryption, and smart contracts or blockchains. So let's take a look at the kind of architecture story or how we came to the architecture that we're currently looking for the OpenMined platform. And really where this conversation begins is the the kind of standard AI business model. So we have this corporation called AI Incorporated, and they have all of their data and all of their machine learning models all in one place. And this is really great for them because they can just train it all at once and they're happy. However, it requires invading the privacy of Jane, Joe, and Jack, who had to upload their data to AI Incorporated, and AI Incorporated now kind of controls it. So the first proposal of the kind of architecture is for federated learning. So let's say when we combine deep learning and federated learning, what does it look like? So we have AI Incorporated with this initial model, and it's red to show that it kind of stinks, right? It's not very good. So it sends it down to Joe. Joe gets it. Using his own data, he improves the model and submits the gradients back to AI Incorporated. So now AI Incorporated has a slightly smarter model. Then he does the same with Jane, and the model becomes even smarter. And the same with Jack, and the model becomes even smarter. And he finishes with this very smart model, and the benefits were he didn't actually have to see Joe, Jane, or Jack's data, right? So it might be looking like, oh my gosh, this is perfect. We're basically done. Everyone got to keep their data secret. Privacy was not invaded. That was awesome. However, these gradients, these updates to the model weights, can give hints about what is likely contained inside the data. So it's actually quite dangerous for AI Incorporated to actually see these updates that Joe is making, because they sort of imply the kind of data that Joe was working with. And there's this whole field of study called differential privacy that's trying to make it so that these gradients don't give those hints. However, it's still a little bit of an open problem within machine learning research. Second, and this is the big one, is that Joe, Jack, and Jane could all steal the model, right? So AI Incorporated sent them the model, right? He's got a copy of it down here. At that point, he can just take it, right? Now at this point, it's not very smart, but when he gives it to Jane and then to Jack, Jack has the final model, like the one that AI Incorporated was trying to train the whole time, and so if AI Incorporated was like a medical institution who wanted to train, a cancer research application that's worth $1 million, right? Jack all of a sudden has this $1 million asset decrypted sitting on his hard drive that he's just supposed to kind of not sell to anyone else, right? So it kind of creates this problem that AI Incorporated, using just federated learning, can't actually train any really valuable models, right? You can do maybe cursory models or things that are sort of out in the open already, but there's this sort of capitalism problem where the models are put at risk, and so really valuable models can't be trained with just deep learning and federated learning. Finally, it's a blind marketplace. Like AI Incorporated is working with each one of these parties in isolation. We have no idea whether each one is being compensated fairly, and establishing a market price is kind of impossible because it's not an open marketplace. So let's add in homomorphic encryption and see what we get. So training a machine learning model is fundamentally a series of additions and multiplications and a few other functions, right? So what if before AI Incorporated sent the model to Joe, he homomorphically encrypted it in this little purple cloud of homomorphic encryption? So he sends the encrypted model to Joe. Joe then increases the intelligence of the model. He trains the model on his own data in a homomorphically encrypted state. So Joe can't actually read the values, but he can make it a little bit smarter. He then sends the gradients that are also homomorphically encrypted back up to AI Incorporated. And the same is repeated for Jane and for Jack. Well, this is perfect, right? Because AI Incorporated was able to generate the model that they wanted to train. Jane, Joe, and Jack never actually had a copy of the model they could use. It was always encrypted. And at the very end, AI Incorporated ends up with the same model that was very, very intelligent. And this might seem like the perfect system, and it really is a lot of progress, right? This is a really, really compelling model. People are able to keep their data secret. The model is protected from theft, and we can form profitable business on this because since the models can't be stolen, we can now train valuable models. AI Incorporated can train valuable models on the decentralized data. The cons are, however, since an encrypted model is actually being sent to people's data sets, in my personal research at Oxford, I study long-term memory. Long-term memory includes the ability for neural models to just memorize the data set, right? So what if when AI Incorporated sent it down to Jack, he sent down a model that just memorized Jack's data and then went back up to AI Incorporated. AI Incorporated just stole Jack's data and used the model as a carrying device, right? As basically a mule for his data. That is not what we want. And it was only possible because the model was encrypted, because Joe, Jack, and Jane can't actually see it and know what's going on under the hood to see whether their data is being copied. So that's part of this this kind of new issue. The final one is this is a blind marketplace, right? So we still don't have any competition on price, and that's something that we would like to be able to see in this platform. Okay, so finally, we're going to look at what if we have deep learning, federated learning, homomorphic encryption, and smart contracts to try to mitigate a little bit of this risk. So this is getting pretty close to the final vision for the OpenMined platform at a very high level. So we have this happy data scientist who has a little bit of money, and he uses what's called the data science client. In this case, this is PySonar, or the Sonar user interface. And this interface allows AI Incorporated to train machine learning models using kind of a friendly user interface. So this starts off with AI Incorporated sending a model spec, or I want to train logistic regression, or I want to train RNN, basically a general description of what the desired model to train is, along with a little bit of money to a smart contract. So that spec sits right here, the money sits right here, and the smart contract initializes the model itself. Now, here's why this protects someone from using the model as a data carrying mule. Because the weights are randomly initialized by the smart contract, and all of the information used to initialize those weights is public, then there aren't any kind of hidden secrets inside the homomorphic encryption that AI Incorporated can embed to make it so that it secretly memorizes data. Now, he could just call for an architecture that does data memorization, but it would be really obvious, and we as the platform can build a preventative measure for that. So smart contract homomorphically encrypts the model, and then mine requests description of all available models. Okay, so this is Joe's data in a data mine, right? This is a place where he is hosting it. The first thing that he does is he requests a description of all models that are available and receives those specs, right? And then he goes, I think this is a compatible model with some of the data that I have. I am going to try to train a model on this. So he requests the model parameters, they get sent down, and then Joe makes it smarter. See how it turns from red to green? He makes it smarter by training it on his own data, sends the gradients back up into the smart contract. So now the smart contract evaluates those gradients and says whether they are valuable or not. So it's a good gradient. So Joe gets rewarded with a little bit of cryptocurrency. Cool. So Joe just made some money. The model became a little bit smarter, and everyone seems to be protected, right? And this process obviously repeats with Jack and Jane. So privacy, theft, profitable businesses. Privacy again, because AI can't steal the data maliciously, and that was the new contribution with the smart contract. And even better, it's an open market because all the monetary rewards are transparent. However, there's one new additional problem, and that is that the public-private key generation for the homomorphic encryption. Whoever holds those keys has the ability to decrypt any part of the system at any time. So who should hold on to them, right? Well, it can't really be the blockchain because it's 100% transparent, right? Anyone can see everything that's inside this blockchain. So if it holds the keys for homomorphic encryption, well then anyone can decrypt the models or the gradients or anything, right? Nothing is safe. We just kind of broke the whole system, right? Whereas if it's the miners, no, they could decrypt the model and steal the model. And if it's AI incorporated, well, no, they could decrypt the gradients and then learn with the gradients. We need a third party that hangs on to these keys. And so for that, we propose using what's called an oracle. Cool? So AI Incorporated starts out with everything he did before, as well as a public RSA key, right? And this is just going to be something he's going to use at the end. We'll see how that works. So he starts by sending the spec and the money to the smart contract. So I want to train a linear regression model, and I want it. And here's how much money here's the bounty I'm willing to reward miners for helping me train it, and then this key, which we're going to use later. It sends the model spec to an oracle, which is a third party. Think of this just like a Amazon Web Services black box, right? No one can hack in, and it just does the same thing over and over and over again, and we'll show you why it's a trusted party in a minute. So it generates public key and private key, and it generates the model. It encrypts the model, and sends it back to the smart contract with the public key, the homomorphically encrypted public key. Okay? Now, the same process that we saw before executes. Good gradient, reward with money. And then once we're done, the model goes down, the final model goes down to the capsule, it's decrypted, and then encrypted with the RSA key, right? The one that AI Incorporated is the only person who knows how to decrypt. That goes back out to the smart contract and gets sent back to AI Incorporated, who can then decrypt it. Okay? So, because this Oracle capsule is holding onto the keys and is not, one of these two parties, no individual person ever has the ability to decrypt either the model or the gradients. Now you might be asking, who can we trust? So the working platform that we have for this is that there's actually another smart contract that operates as an insurance policy. So if, say, Amazon Web Services or some other party wants to be a capsule, they have to put up money at risk, right, into another smart contract. And what that basically means is that if anyone can figure out what this private key is, then they will automatically earn a bounty of $1 million that's taken from the person hosting the capsule service, right? So the idea is that if I'm hired to protect all these private keys, I have to put a bunch of money at risk such that if I gave the key to anyone, they would steal that money and I would lose $1 million, right? So to financially incentivize. And it's really it's an insurance policy against them sharing these particular secrets. And that's the model that we're going forward with in this first version of OpenMined. So how can I build this? Go check out the website. Here are the first initial libraries, what they're all about. And really, yeah, just go hop on the website, openmind.org, hop into the Slack. Feel free to message me on Twitter or via email. And that's kind of how we're going to move forward. So thank you so much for your attention. I hope this has been very enlightening for you, and I look forward to seeing your questions on Slack. Have a great day.